Okay, so I'm going to keep talking about kind of these two-phase processes, but I'm going to be looking at ice-ocean interfaces and how some of the microphysics that are occurring at this interface are going to determine things like impurity entrainment, things like salts, and how that can affect things like geodynamics and different geological features. So I'm going to kind of introduce this idea of these frozen fingerprints. And the idea for this is that in the general sense, fingerprints are this like small piece of evidence that if you do your analysis right, you can really reconstruct kind of a very intricate picture of what happened just using a kind of like a small piece of evidence. And that's kind of something that's already used in the ice community for things like looking at ice cores and looking at ash layers to reconstruct past volcanic events, or things like looking at gases and chemistries in ice cores to reconstruct things like paleoclimate. The idea here is that can we do that for things like ice-ocean worlds? Um, when you're thinking about things like composition and thermodynamics that are happening in the ocean, can those things be basically trapped and recorded in the ice shell? And so that's kind of going to be what we're looking at today. I'm going to look at Europa mainly because that's, I think, a really good archetype for this process, especially because you have all these features on the surface that might be indicative of these kind of like endogenic processes and materials that are getting brought up in these red bands and things like this. So the idea here is that you have all these processes that are occurring in the ice shell, but really what we're going to be looking at is this ice-ocean interface down at the bottom here as kind of this location where information about the ocean and what's occurring at this interface is going to get trapped in and kind of determine what this ice is going to look like. So the main idea behind this is that at these interfaces, when you're freezing out an ocean, it doesn't freeze out like pure water does. When you freeze out pure water, you basically just get this single solid phase block of ice, and you can really just conduct heat through it, but you don't have any fluid transport. When you start solidifying things that have solutes in them, you start getting these two-phase systems where the ice component of your mixture is going to freeze out, and all of these solutes are going to get rejected, and you end up with kind of this porous medium where you can have like these brine channels and things like this. And this is just fresh water and salt water. And when you put food coloring on the top, you can see that it basically gets sucked up in these little channels and things like that. And that's important because you can have two-phase transport in there, but you also have two different phases. You have liquid and solid, and they're going to have different things like thermal properties, things like that. Another way to think about this is it's something that happens in magmatic systems. And I think this is important to think about in these like cryovolcanic, cryomagmatic systems, is that when you have a magma of one composition, you start to cool it down, you start to fractionally crystallize out these different components. And as that happens, you kind of form this two-phase slushy layer here, and your brine is also going to change. The same thing's happening in this ice system where you have this ocean below, and once you start to crystallize out the ice, the brine in this kind of interstitial pore space is going to change. And so this is actually an image of laboratory grown sea ice where you can see the pure fluid down below, kind of more solid up the top, and you actually get these drainage channels where this dense brine is actually flowing out into the underlying liquid. You can also see kind of these little pockets of fluid and stuff like that, and there's a definite gradient in kind of your composition there. So in the case of Europa, it's kind of a problem of scale because a lot of these processes are happening on this very small centimeter scale resolution things, but we're really worried about an ice shell that might be 10 to 30 kilometers thick. Same with all these processes that we think impurities might be an important part of. Things like subduction. Brandon Johnson wrote a paper that said, well, if we have heterogeneous salinities in two different lithospheric slabs, that could be a way to initiate subduction. It's also suggested as a way that you could get these convection cells if you have this thermocompositional convection where you have this fresher, warmer ice kind of upwelling and the colder ice downwelling. Brittany has also talked about potentially having these eutectic surfaces where if you can trap high concentrations of salt somewhere in the shell, it could kind of promote this melting of these lenses. And lastly, I wanted to look at something from Earth where we see this too in ice shelves down in Antarctica where stuff's actually sliding off the continent. This is a meteoric ice shelf, and you can see the bottom surface reflection of this radargram here, but then it kind of disappears because you actually have this brine layer that's infiltrating back in. And so what's happening is this radar is coming down, it's actually bouncing off that brine layer and kind of hiding everything underneath. So that's going to be important for things like rhyme and reason in these future missions. So one of the problems here is that these impurities are definitely important for kind of these geodynamic processes, but there's not really been a physical way to constrain how much of these impurities are actually getting sucked up into the ice during the formation of the ice shell. So that's kind of what we're going to be looking at down in this interface, which is really going to determine where components of the ocean are going to get trapped within the shell. So how we did that is we did a one-dimensional model. There's a few different pieces to it. The first part is using this mushy layer theory. We basically are conserving heat and mass and fluid processes that are creating this layer using mushy layer theory. It's basically just a continuum mechanics model. On top of that, we wanted to take into account that you get this convective overturn of this dense brine down at the bottom. So we're using a 1D parameterization that's used a lot in sea ice models, and it's been very successful. Lastly, we're going to actively track the interface. Because it's such a thick ice shell, we really only are concerned about that kind of slushy two-phase layer at the base of the model. So we're going to consider this critical porosity kind of like Noah did, where once a layer hits this level, we consider it impermeable and kind of take it out of the system. We're going to follow that slushy layer as we're freezing the ice shell out. So this is basically what we produced. So the first thing we did is we wanted to see if the model works, so we're going to compare it to sea ice on Earth. And so these are basically the profiles that the model can produce. So the time is on the x-axis and your depth is on the y-axis, and so you get an evolving temperature profile, an evolving liquid fraction profile, salinity, and then the total salt, which is just the liquid fraction times the salinity. So at the end of this, you can basically take a slice at the end of this ice, and it's basically like drilling an ice core, which you would do down on sea ice or something in Antarctica. And we can compare that salinity profile, which is in the dash and the solid lines here, with actual measurements, which is the red and the open circles here. And so it matches really well. So we're confident that we're accurately modeling how much of the ocean salt is getting trapped in the ice. So for the Europa environment, we also wanted to take into account different chemistries. So we're simulating both Earth sodium chloride-based oceans and also looking at 3 different concentrations of a magnesium sulfate-dominated ocean. And so this is just a plot of basically we had to get new liquidus curves, and so this is using freeze chem to basically produce different relationships for your basically precipitation point of ice based on your concentration for the magnesium sulfate ocean. So the main goal of this was basically to produce these profiles of salt in the European ice shell and relate them to what was happening at the interface when this ice was formed. Really looking at things like the thermal gradient at the interface and how that influences how much salt gets trapped in the ice. And can we come up with a relationship that relates these two things? Because then you can directly apply that to a bunch of different scenarios on these ice ocean worlds without actually having to simulate all these small scale reactive transport processes. And so that's what we did. You've got depth down here on the bottom, and then total salt. It only goes down to 400 meters here because what happens is high in the upper ice shell where you have higher thermal gradients, you're trapping a lot of salt, but it quickly approaches this kind of asymptotic limit that's going to be governed by that critical porosity that we set and also the ocean composition. You can take this and you can directly translate that into a plot of thermal gradient, which is down here on the bottom end ice. So the upper ice shell will be here and the lower ice shell will be here. And it actually breaks down into 2 regimes here. You have this kind of more arcuate. There's the linear one down here, and then you have the arcuate one up here. This one is in the upper ice shell, and that's going to be determined by these convective processes and these reactive processes. And then basically towards the bottom, you're going to get to this lower diffusive limit where basically you hit this, this linear line where essentially the pore fluid in this 2-phase system is going to be able to have enough time to equilibrate with the underlying ocean under lower thermal gradient. And so things that you can do with that is you can take these relationships and start getting at things like the total salt in the shell, and you can basically just integrate through something like a 25-kilometer shell and produce estimates of how much salt would be trapped in the shell. That's important for things like the convective overturn in the shell. It's also important for identifying potential locations in the shell where you might have these kind of like buildups of higher salts and things like that. And also for predicting how much salt is near the surface compared to down lower in the shell. Directly related to that is going to be the density of the ice. So basically you can come up with profiles for how dense or for what the density profiles would be in the shell. It's going to look similar where you have this asymptotic drop off. And one of these key points is that the limits for these systems is going to really be set by this ocean salinity and the critical porosity. So I think it's really important, and I think Mark brought this up and Noah brought this up, that these critical porosities and understanding basically how well fluid and brine can flow through the ice is really going to determine how well you can have these multi-phase systems kind of be stable in the ice shell, and also in this case is going to determine how much salt you're actually going to be able to trap in the ice shell. Things for the density, it's important for things like subduction, also potentially forming rheological boundaries within the ice. So if you have this high salt content up higher in the ice, but a pretty homogeneous portion lower in the ice, this might be a region where you can have some kind of mechanical, difference in the ice layer. We also wanted to apply it to fractures, so we modified the model to take into account basal fracture geometry. So if you open up a fracture in the bottom of the ice, because it's going to be high aspect ratio, you're going to have this amplified brine drainage out along the edges of the fractures, and so we can come up with these new relationships between thermal gradient and how much salt's getting trapped in the ice. And then we can basically go through and plot how much salt gets trapped in these fractures as they freeze out. And so as you can see, there's higher salt content along the walls at higher thermal gradients, and that's going to decrease as you go inward. You can also look at basically how this evolves over time. And basically what you get here is the same thing, where you have these high salt contents along the walls of the fractures and less as you go in. And this could be a way to basically, once you open this fracture and refreeze it out, that these walls are solidifying quite quickly. It could be a mechanism for basically forming these heterogeneities in the ice, and it could be a mechanism for these fractures to basically stay active, provide some weakness within the shell. Lastly, we looked at the solidification of lenses in the shell. So if you have this perched lens within the shell, we basically have the background salinity here in the dashed line. So that was the original profile of the ice shell. And then we melted this lens in situ and well mixed it. So it's going to have a lower salinity to begin with. And then as you start solidifying this lens from the top down, you're going to keep freezing out that ice, and you're going to entrain some of that salt in the ice. But any of that salt that doesn't get entrained in the ice is going to get rejected into the lower liquid and produce a higher brine salinity. And so as this freezes out towards the bottom, you get a higher and higher brine salinity to the point where you're actually going to precipitate ice or salt, down along the bottom of the lens. So this is an interesting thing where if you melt water in situ in the lens and then start to re-solidify it, and it's not connected to the underlying ocean, it could be a very concentrating process where you can really localize salt within the shell, which is going to be important for things like water pockets. So the main takeaways from this are that the salt content in the shell or in these brine pockets, when you freeze out this ice, is going to be uniquely determined by the thermochemistry at this interface. Also, the permeability porosity relationships at this interface are really important. So I think constraining these experimentally and things like that is going to be really important for improving these models going forward and understanding how fluids and salts are going to be incorporated and move through the ice shell. And that these impurities within the ice shell are going to be important for a lot of the geophysics that are occurring in these ice shells. And lastly, I'll just leave you some of the stuff that we're working on now. We're actually going up to Canada and looking at these magnesium sulfate hypersaline lakes in Canada to just kind of look at the chemistry and the porosity and things like that, to kind of, on top of the sea ice system, get a look at basically a different composition of ice and see if that's going to look different and behave different than sodium chloride ice. Is another way to basically back up these models, and also look at things like ternary phase systems, where you can have things like hydrated salts precipitate out in these systems, as well as just the ice and the brine. That's it. Thanks.
So we have plenty of time for questions, and then we can transition into discussion.
In terms of generating salt profiles with depth, is it true that I have the sense there's two competing effects? One is sort of the freezing rate, which would, I guess, lead to it gets slower as it goes deeper and would lead to a decrease. But then also there's the concentration of the remaining salt, and that can lead to an increase downward. Is that correct?
Yeah. So for the ocean systems, I basically treated it as an infinite reservoir. So I didn't increase the salinity in the oceans, but for for the lenses I did, so where the pockets were trapped, any of the salt that got rejected from the ice got pushed into the remaining liquid and would basically increase your salinity of the new ice, because even though it's freezing slower, it has more, like a higher salt content in that underlying fluid.
Yeah, I was wondering, what's the chemical difference between the very near surface and the remaining liquid that gets trapped in that last 5%?
What do you mean, the chemical
Like,
difference?
is there a
Like,
difference in chlorine versus magnesium versus sulfur content for the near surface versus the bulk of the ice shell?
okay, so far I've only been doing like the binary system, so one salt at a time. It would be interesting to look at the two systems to see if the diffusivities or the molecular weights or something like that are going to kind of like partition these chemistries into different regions as they're freezing out.
So I'm curious um, about your lower limit salinity for the bulk ice shell. That's about 2 ppt. Can you explain where that comes from?
So basically what happens is, as this freezes out, I set a lower limit on how much fluid flow you can have through the ice. And so when you hit 5% porosity, I basically cut off fluid flow and trap any of the remaining brine in the ice shell.
Right.
As you go down in the shell and you get to thicker layers, your thermal gradients are less. And so basically that asymptotic limit is going to be set by when your thermal gradients are low enough, your pore fluid is actually going to be pretty close to like completely equilibrated with the ocean. And so whatever pore fluid is left is going to be 5% guaranteed, because that's my cutoff when I like incorporate it into the overlying ice shell. And that's just basically going to be at that point the ocean chemistry. So I think it's really important to kind of nail that critical permeability and porosity down, because if you can keep pushing or convecting fluid out of the ice, then that's going to continue to freshen your ice shell. So if you can get basically down to, you know, close to like Mark was showing, if you can actually get down to that like almost zero porosity with a super low permeability, but fluid can still flow, then I think your ice is going to be able to be almost pure, like marine ice kind of purity, if not more.